Hello there, and welcome to Sleep Knowledge. Tonight's journey takes us beyond our world, out into the vast expanse of space, where we'll explore some of the most extraordinary facts about our universe. Some of what we'll discover will be gentle, like the quiet drift of distant moons. Other truths will be powerful, like the birth of stars in cosmic nurseries. But each one carries a wonder stranger than fiction and more beautiful than we could dream. This evening, we'll wander through a collection of cosmic truths and celestial mysteries, glimpses into worlds where time bends, where galaxies dance, and where the laws of physics create phenomena beyond imagination. You might find yourself drifting off to sleep or simply relaxing with this in the background. If you enjoy these gentle explorations and would like to join us for more nighttime journeys, you can like and subscribe to Sleep Knowledge, and feel free to share your thoughts in the comments below. But for now, all you need to do is get comfortable. Let your breathing slow, your mind settle, and allow the universe itself to wrap around you. Let's begin. The universe is still expanding from the Big Bang. About 13.8 billion years ago, the universe began from an infinitely small, infinitely dense point. In a fraction of a second, it expanded faster than the speed of light in an event called cosmic inflation. Space itself stretched, carrying matter and energy outward in all directions. And remarkably, this expansion hasn't stopped. Today, galaxies continue moving away from each other, pushed by a mysterious force called dark energy. The farther away a galaxy is, the faster it appears to recede. This means the universe is not only vast, it's growing vaster every moment. Astronomers can measure this expansion by observing how light from distant galaxies shifts toward the red end of the spectrum, a phenomenon called redshift. It's evidence written in starlight that our cosmos is dynamic, evolving, and far from finished with its story. When we look at the night sky, we're seeing not just where things are, but where they were. And tomorrow, they'll be a little farther away. Light from distant stars takes years to reach us. When you look up at the night sky, you're seeing the universe as it was, not as it is. Light travels at about 300,000 kilometers per second, incredibly fast. Yet the distances in space are so vast that even light takes time to cross them. The light from our sun takes about 8 minutes to reach Earth. Light from the nearest star beyond the sun, Proxima Centauri, takes over 4 years. And light from distant galaxies can travel for billions of years before arriving at our telescopes. This means when we observe a galaxy 10 billion light years away, we're seeing it as it appeared 10 billion years in the past, when the universe was young and stars were just beginning to form. In a very real sense, telescopes are time machines. They allow us to look back through cosmic history, witnessing the birth of stars, the collision of galaxies, and the evolution of the universe itself. The night sky is not just a map of space. It's a timeline stretched across the heavens. There are more stars in the universe than grains of sand on Earth. Try to imagine every beach, every desert, every handful of sand on our entire planet. Now multiply that by 100. That's roughly how many stars exist in the observable universe. Current estimates suggest there are about 200 billion trillion stars, a number so large it's nearly incomprehensible. Each one is a sun, potentially with its own system of planets, moons, and cosmic weather. The Milky Way alone contains between 200 and 400 billion stars, and it's just one galaxy among billions. When we look up at the night sky, we see only a tiny fraction of what's out there. Most stars are too faint, too far, or hidden behind dust and gas. But they're there, burning, evolving, dying, and being born again. This abundance is humbling. It reminds us that we live in a universe of almost infinite variety, where each point of light represents a world unto itself, with its own story unfolding across time. Black holes can warp space and time. In the presence of a black hole, the fabric of space-time itself bends and distorts. Gravity near a black hole is so intense that nothing, not even light, can escape once it crosses the event horizon, the point of no return. But the effects reach far beyond that boundary. Time slows down near a black hole. To an outside observer, someone falling toward the event horizon would appear to move slower and slower, eventually seeming to freeze in place. Yet from the perspective of the person falling, time passes normally. It would cross the horizon and continue inward, unaware of the strange dilation happening from an outside view. This warping of time and space has been confirmed through observations and experiments. It's not science fiction. It's a fundamental property of the universe, predicted by Einstein's general theory of relativity. Black holes are places where the rules change, where gravity becomes so extreme that it reshapes reality itself. Some planets orbit two suns. In binary star systems, where two stars orbit each other, planets can form in orbits around both stars. These are called circumbinary planets, and they experience double sunrises and sunsets. Imagine standing on such a world and watching two suns climb above the horizon, casting twin shadows across the landscape. The gravitational dynamics of these systems are complex. The planet must orbit far enough from the binary pair to remain stable, or it would be torn apart by competing forces. Yet many such worlds have been discovered, proving that planetary systems are far more diverse than we once imagined. The climate on a circumbinary planet would be unusual. Depending on the star's brightness and distance, seasons might fluctuate wildly, or one sun might dominate while the other provides only a faint secondary glow. These alien skies remind us that the universe doesn't follow a single template. It explores every possibility. The sun is just an average star. From Earth, the sun appears unique, the brightest object in our sky, the source of all warmth and light. But in the cosmic context, it's remarkably ordinary. It's a G-type main sequence star, neither particularly large nor small, hot nor cool. Billions of stars in the Milky Way are similar. Some are larger, burning hotter and brighter, but living shorter lives. Others are smaller, cooler, and can shine for trillions of years. The sun sits comfortably in the middle, with a lifespan of about 10 billion years. It's currently halfway through that span, steadily fusing hydrogen into helium in its core. This ordinariness is, in a way, fortunate. If the sun were much larger, it would have burned out long before life had a chance to evolve on Earth. If it were much smaller, Earth might be too cold to support liquid water. The sun's mediocrity is what makes it perfect for us. And somewhere out there, among the countless stars, there are likely other ordinary suns with their own planets, perhaps hosting their own forms of life. Galaxies collide, but stars rarely do. When two galaxies merge, it sounds catastrophic, and in many ways, it is. Gravity pulls the galaxies together, their shapes distorting into tidal tails and arcs. Gas clouds compress, triggering bursts of star formation. Supermassive black holes at the centers spiral toward each other, eventually merging in a release of gravitational waves. Yet despite all this chaos, individual stars almost never collide. The distances between stars are so vast that they simply pass by each other, like fireflies drifting through a vast, dark field. Over hundreds of millions of years, the two galaxies blend into one, their stars mixing, their gas clouds merging, their histories intertwining. The Milky Way itself is on a collision course with the Andromeda Galaxy. In about 4 billion years, they will merge, forming a larger galaxy sometimes called Milkomeda or Milkdromeda. Our Sun, if it still exists then, will likely survive the event unscathed, finding itself in a new orbit within the merged system. From Earth, the night sky during this merger would be breathtaking, filled with brilliant arcs and streams of stars. Neutron stars are incredibly dense. When a massive star exhausts its fuel and collapses, it can leave behind a neutron star, an object about 20 kilometers wide but more massive than the Sun. The matter inside is so compressed that protons and electrons merge into neutrons, creating a density almost beyond comprehension. A single teaspoon of neutron star material would weigh about 1 billion tons on Earth. The gravity at the surface is immense, warping space and bending light. Some neutron stars, called pulsars, spin hundreds of times per second, emitting beams of radiation from their magnetic poles. As they rotate, these beams sweep across space like a lighthouse, and if Earth happens to lie in their path, we detect regular pulses, sometimes more precise than atomic clocks. Neutron stars are the edge of what matter can become before collapsing into a black hole. They're laboratories of extreme physics, places where our understanding of the universe is tested and expanded. There are planets made almost entirely of diamond. Deep within certain gas giants and ice giants, the pressure and temperature are so extreme that carbon atoms can be compressed into solid diamond. On planets like Neptune and Uranus, scientists believe it might rain diamonds, crystallized carbon falling through layers of gas before eventually melting in the hotter depths. Laboratory experiments on Earth have recreated these conditions, using lasers to compress hydrocarbons into tiny diamonds. The physics is sound, and if it happens in our solar system, it likely happens elsewhere. Some exoplanets, particularly those rich in carbon, might have entire layers of diamond deep within their interiors. We'll never mine these treasures, of course, but knowing they exist transforms these distant worlds in our imagination. They become glittering, alien landscapes, places where the familiar is rendered extraordinary by sheer extremity. The moon is slowly drifting away from Earth. Every year, the moon moves about 3.8 centimeters farther from our planet. This happens because of tidal forces. As the moon's gravity pulls on Earth's oceans, it creates bulges of water that move around the planet. These tidal bulges exert a drag on Earth's rotation, slowing it down while simultaneously transferring energy to the moon, nudging it into a higher orbit. Billions of years ago, the moon was much closer and Earth's days were much shorter. Fossil records and ancient coral growth patterns confirm this. A day on early Earth lasted only about 10 hours. Over time, as the moon drifted outward, days lengthened to the 24 hours we experience now. In the far future, this process will continue. Eventually, Earth and the moon will become tidally locked, with one side of Earth always facing the moon, just as one side of the moon always faces Earth. But that's billions of years away. For now, the moon continues its slow, graceful retreat, a reminder that even the most familiar features of our world are not permanent. Mars has the tallest volcano in the solar system. Olympus Mons on Mars rises nearly 22 kilometers above the surrounding plains, making it almost 3 times the height of Mount Everest. It's not just tall, it's also massive, spanning roughly 600 kilometers across, about the size of the state of Arizona. This shield volcano formed over millions of years as lava slowly built up layer by layer. Mars' lower gravity and lack of tectonic plate movement allowed it to grow far larger than any volcano on Earth. On Earth, volcanic hotspots like those that form the Hawaiian Islands move as tectonic plates shift, creating chains of volcanoes. But on Mars, the crust stayed in one place. allowing Olympus Mons to keep building upward and outward. Though it's considered dormant, some geological features suggest it might not be entirely dead. Standing at its base, the summit would be invisible beyond the curve of the planet. It's a monument to the geologic power of an entire world, frozen beneath the rust-colored Martian sky. Saturn's rings are disappearing. The beautiful rings of Saturn, composed mostly of water ice mixed with rock and dust, are not permanent. They're being pulled inward by Saturn's gravity, falling toward the planet in a process called ring rain. Tiny particles collide and lose energy, spiraling slowly down into Saturn's upper atmosphere, where they vaporize. At the current rate, the rings could vanish in as little as 100 million years, a blink in cosmic terms. Observations from the Cassini spacecraft revealed that the rings are much younger than Saturn itself, possibly only a few 100 million years old. They may have formed from the breakup of a moon or comet that wandered too close. For now, they remain one of the most stunning sights in the solar system. Gleaming bands of ice that catch sunlight and shimmer across the void. But they are temporary, a fleeting display of beauty in an ancient system. There are storms on Jupiter that have raged for centuries. The Great Red Spot, a massive storm on Jupiter, has been observed for over 300 years. It's an anticyclone, a high-pressure region where winds spiral at hundreds of kilometers per hour. At its largest, it was big enough to fit 3 Earths inside. Recently, it's been shrinking, but it still dwarfs any storm on our planet. Jupiter's storms are powered by the planet's rapid rotation and internal heat. Unlike Earth, where storms lose energy when they hit land, Jupiter has no solid surface, allowing storms to persist for decades or centuries. The Great Red Spot's reddish color is thought to come from complex chemical reactions in the upper atmosphere, possibly involving sulfur or phosphorus compounds. Other storms, some nearly as large, continue to churn across Jupiter's face. The planet is a world of constant atmospheric drama, a laboratory for studying weather systems on a scale we can barely imagine. Space is not completely silent. In the vacuum of space, sound waves can't travel because there's no air to carry them. But space is far from silent in other ways. Electromagnetic waves, such as radio waves, pass through space constantly. Astronomers can convert these signals into sound, allowing us to hear the universe. The sun emits a constant hum of radio noise. Pulsars create rhythmic clicks. Black holes, when they devour matter, produce bursts of radiation that can be turned into eerie tones. Even the cosmic microwave background, the afterglow of the Big Bang, has been translated into sound, revealing the faint echo of the universe's birth. These sounds aren't meant for human ears, but they give us another way to experience the cosmos. In a very real sense, the universe is full of music, vibrations, and rhythms. We just need the right instruments to listen. Some moons have subsurface oceans. Beneath the icy crusts of moons like Europa, Enceladus, and Ganymede, scientists believe there are vast oceans of liquid water. These oceans are kept from freezing by tidal heating, the friction generated as the moon flexes under the gravitational pull of its planet. Europa, a moon of Jupiter, may contain more water than all of Earth's oceans combined. Its surface is covered in cracks and ridges, suggesting that the ice shell is dynamic, shifting as the ocean beneath moves and churns. Enceladus, a moon of Saturn, has geysers that spray water vapor and ice particles into space, feeding Saturn's faint E-ring. These plumes have been detected by spacecraft and analyzed for chemical composition. They contain not just water, but also organic molecules and salts, ingredients that could support life. These hidden oceans are some of the most promising places to search for extraterrestrial life in our solar system. They remind us that life doesn't need sunlight to thrive. It just needs water, energy, and the right chemistry. The coldest place in the universe isn't in deep space. You might think the coldest temperatures would be found in the empty voids between galaxies, but the coldest known place is actually the Boomerang Nebula, a cloud of gas about 5,000 light years from Earth. Temperatures there drop to just 1 degree above absolute zero, colder than the faint background radiation left over from the Big Bang. This extreme cold occurs because gas from a dying star is expanding so rapidly that it cools beyond the ambient temperature of space itself. The nebula glows faintly in visible light but shines brightly in radio wavelengths. Its hourglass shape is the result of stellar winds and jets from the central star. Eventually, the star will heat up again, dispersing the nebula. But for now, it remains the universe's deepest freeze, a natural cosmic refrigerator preserving its contents in near absolute stillness. Gravitational waves ripple through space-time. When two black holes or neutron stars spiral toward each other and merge, they create ripples in the fabric of space-time itself. These are called gravitational waves, and they travel outward at the speed of light, stretching and compressing space as they pass. On Earth, detectors like LIGO can measure these tiny distortions, changes smaller than a fraction of an atom's width. The first detection of gravitational waves in 2015 confirmed a major prediction of Einstein's general relativity and opened a new way of observing the universe. These waves carry information about events we could never see with light alone: the collision of black holes, the mergers of neutron stars, and possibly even echoes from the Big Bang itself. Listening to gravitational waves is like hearing the universe's heartbeat, a deep rhythm that underlies all cosmic events. Stars are born in clouds of gas and dust. Across the galaxy, vast molecular clouds drift through space, composed mostly of hydrogen with traces of other elements. These clouds can span hundreds of light years and contain enough material to form thousands of stars. Over time, regions within the cloud begin to collapse under their own gravity. As the material compresses, it heats up, eventually becoming dense and hot enough to ignite nuclear fusion. A star is born. The process doesn't happen in isolation. Stars often form in clusters, with dozens or hundreds igniting at roughly the same time. The leftover material around a young star can coalesce into planets, moons, asteroids, and comets, forming a complete solar system. Our own sun formed this way about 4.5 billion years ago in a cloud that also gave birth to other stars, now scattered across the galaxy. Looking at stellar nurseries today, we're witnessing the process that created our own world, frozen in different stages across the cosmos. Planets can be ejected from their solar systems. Not all planets stay in orbit around their stars. Gravitational interactions, particularly in systems with multiple large planets, can sometimes fling a planet out into interstellar space. These rogue planets wander the galaxy alone, no longer bound to any star. Without a sun, they drift through eternal night, their only warmth coming from residual heat from their formation or radioactive decay deep inside. Some may still have thick atmospheres or subsurface oceans insulated by ice. Estimates suggest there could be billions of rogue planets in the Milky Way, possibly outnumbering stars. They're incredibly difficult to detect because they don't reflect starlight, but astronomers have begun finding them using gravitational microlensing, watching for the brief dimming of background stars as a rogue planet passes in front. These wanderers are reminders that planetary systems are dynamic, sometimes chaotic, and not always stable over cosmic time. White dwarfs are the remnants of stars like our Sun. When a star like the Sun exhausts its nuclear fuel, it swells into a red giant, shedding its outer layers into space. What remains is the core, a dense, hot object called a white dwarf. It's about the size of Earth, but contains roughly half the Sun's mass. With no fusion occurring, a white dwarf doesn't generate new energy. It simply cools over billions of years, fading slowly from white to yellow to red to black. This cooling process is so slow that the universe isn't old enough yet for any white dwarf to have fully cooled into a black dwarf. White dwarfs are incredibly dense. A sugar cube-sized piece would weigh about a ton. They're held up not by fusion or ordinary pressure, but by electron degeneracy pressure, a quantum effect that prevents further collapse. In about 5 billion years, our sun will become a white dwarf, a fading ember, marking the end of its stellar life. The Andromeda Galaxy is on a collision course with the Milky Way. Right now, the Andromeda Galaxy is over 2 million light-years away, the most distant object visible to the naked eye. But it's moving toward us at about 400 kilometers per second. In roughly 4 billion years, it will collide with the Milky Way. This won't be a violent crash in the traditional sense. Stars are so far apart that few, if any, will physically collide. Instead, the galaxies will pass through each other, their gravity pulling them into new shapes. Streams of stars will arc out into space. Gas clouds will compress, igniting bursts of new star formation. Over hundreds of millions of years, the two galaxies will merge, forming a single, larger elliptical galaxy. Our sun, if it still exists, will find itself in a new orbit, possibly farther from the galactic center. From Earth, the night sky during this event would be spectacular, filled with glowing nebulae and brilliant new stars. But by then, Earth itself may no longer be habitable, as the aging sun will have already begun to expand. Red giants can swallow their own planets. When a star like the sun runs out of hydrogen in its core, it begins fusing hydrogen in a shell around the core. This causes the star to expand dramatically, becoming a red giant. The sun, for example, will swell to a size that could engulf Mercury, Venus, and possibly Earth. These outer layers are tenuous, more like a glowing fog than solid material, but they're hot enough to vaporize anything they touch. Planets caught within this expansion are doomed, slowly spiraling inward as they experience drag from the star's outer atmosphere. Eventually, they plunge into the core and are destroyed. This is the likely fate of Earth in about 5 billion years. The sun will grow, brighten, and heat our planet until oceans boil away and the surface becomes molten. Long before the sun becomes a red giant, Earth will already be uninhabitable. But it's a reminder that even stars have life cycles, and their deaths can reshape entire systems. Some stars explode as supernovae, when a massive star, at least 8 times the mass of the sun, exhausts its nuclear fuel. Its core collapses in a fraction of a second. This collapse triggers a supernova, an explosion so powerful it can briefly outshine an entire galaxy. The outer layers are blasted into space at speeds of thousands of kilometers per second, enriching the surrounding interstellar medium with heavy elements. These elements, everything from carbon to iron to gold, are the building blocks of planets and life. Without supernovae, the universe would be composed only of hydrogen and helium, with no possibility of rocky worlds or complex chemistry. The energy released in a supernova is staggering. In just a few seconds, it can emit more energy than the sun will produce in its entire 10 billion year lifetime. The remnant left behind can be a neutron star or, if the original star was massive enough, a black hole. Supernovae are both endings and beginnings, death giving rise to new possibilities. Dark matter holds galaxies together. When astronomers measure the speed at which stars orbit the centers of galaxies, they find something strange. The stars are moving too fast. Based on the visible matter, galaxies, stars, gas, and dust, they should fly apart, but they don't. Something invisible is holding them together. That something is dark matter, a mysterious substance that doesn't emit, absorb, or reflect light. We can't see it directly, but we can infer its presence from its gravitational effects. Dark matter makes up about 85% of the matter in the universe. It forms vast halos around galaxies, providing the gravitational scaffolding that shapes cosmic structures. Despite decades of research, we still don't know what dark matter is. It could be composed of exotic particles that barely interact with normal matter, or it could be something even stranger. Detecting it directly is one of the great challenges of modern physics, but its existence is undeniable, written in the motions of galaxies across the universe. The universe has no center. It's natural to imagine the Big Bang as an explosion from a single point, with galaxies flying outward from that spot. But that's not quite right. The Big Bang didn't happen in space. It happened to space. The entire universe expanded everywhere at once, and it continues to do so. This means there's no central point, no place where the expansion began. Every point in the universe can be thought of as the center, because from any location, distant galaxies appear to be moving away. It's like the surface of an expanding balloon, where every dot on the surface moves away from every other dot, but there's no single point on the surface that's the center of the expansion. The true center, if it exists, would be in a higher dimension, beyond our ability to perceive. This idea challenges our intuition, but it's one of the fundamental truths of modern cosmology. Comets are icy remnants from the early solar system. Comets are often called dirty snowballs, chunks of ice, rock, and organic molecules left over from the formation of the solar system. Most reside in distant regions like the Kuiper Belt or the Oort cloud, far beyond the orbit of Neptune. Occasionally, gravitational interactions nudge a comet inward toward the sun. As it approaches, solar radiation heats the ice, causing it to sublimate and release gas and dust. This creates the comet's characteristic tail, which can stretch for millions of kilometers. The tail always points away from the sun, pushed by solar wind and radiation pressure. Comets are time capsules, preserving material from over 4 billion years ago. Studying them gives us clues about the chemistry and conditions of the early solar system. Some scientists even believe that comets delivered water and organic molecules to early Earth, playing a role in the origins of life. The Milky Way is part of a larger structure. Our galaxy doesn't float alone in space. It's part of the Local Group, a collection of over 50 galaxies, including Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. The Local Group itself is part of the Laniakea supercluster, a massive structure containing over 100,000 galaxies. And Laniakea is just one of countless superclusters in the observable universe. These structures form a cosmic web, with galaxies clustered along filaments of dark matter, separated by vast voids of near-empty space. Gravity pulls galaxies together over time, building larger and larger structures. On the largest scales, the universe looks like a foam, with dense walls and filaments surrounding empty bubbles. Understanding this structure helps us trace the history of the universe, from the tiny density fluctuations in the early cosmos to the grand architecture we see today. Time passes differently depending on where you are. According to Einstein's theory of relativity, time is not absolute. It flows at different rates depending on how fast you're moving and how strong the gravitational field is. Near a massive object like Earth, time passes slightly slower than it does farther away. This effect is tiny, but measurable. GPS satellites, for example, must account for time dilation because time ticks faster in orbit than on the ground. Near a black hole, the effect becomes extreme. Time slows dramatically, and to an outside observer, someone falling toward the event horizon appears to freeze. But from the person's perspective, time continues normally. This means now isn't the same everywhere in the universe. Different observers can experience different flows of time. It's a strange, counterintuitive idea, but it's been confirmed by countless experiments. Time, like space, is flexible. The cosmic microwave background is the oldest light in the universe. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before that, it was a hot, dense plasma where photons couldn't travel freely. But once atoms formed, light was released, filling the universe with a glow. That light has been traveling ever since, stretched by the expansion of the universe into microwave wavelengths. Today, it's called the cosmic microwave background, and it's visible in every direction we look. It's a snapshot of the infant universe, showing tiny fluctuations in temperature that would later grow into galaxies and clusters. Studying the CMB allows us to measure the age, composition, and shape of the universe with remarkable precision. It's a faint whisper from the dawn of time, still echoing through space after more than 13 billion years. Asteroids and comets pose a real threat to Earth. Throughout history, Earth has been struck by asteroids and comets. Some impacts have been catastrophic, like the one that contributed to the extinction of the dinosaurs 66 million years ago. That asteroid was about 10 kilometers wide, and its impact released energy equivalent to billions of atomic bombs, triggering wildfires, tsunamis, and a global winter that lasted years. Smaller impacts happen more frequently. In 2013, a meteor exploded over Chelyabinsk, Russia, releasing energy equivalent to about 30 Hiroshima bombs and injuring over 1,000 people from shattered glass. Fortunately, most asteroids pass by harmlessly. NASA and other agencies track near-Earth objects, cataloging their orbits to predict potential threats. In 2022, NASA successfully tested a planetary defense system by crashing a spacecraft into an asteroid to change its trajectory. It's reassuring to know we're not entirely helpless, but it's also a reminder that space can be dangerous, and Earth exists in a cosmic shooting gallery. Pulsars are the universe's most precise clocks. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space like a lighthouse. If Earth is in the path of the beam, we detect regular pulses of radio waves, sometimes hundreds of times per second. The timing of these pulses is extraordinarily precise, often more accurate than atomic clocks. Some pulsars have been observed for decades, and their pulse rate remains constant to within microseconds. This precision makes pulsars useful for testing theories of gravity, detecting gravitational waves, and even for navigation. In the future, spacecraft might use pulsars as cosmic beacons, triangulating their position by measuring the timing of pulses from multiple sources. It's a beautiful example of how the universe provides tools we didn't know we needed. Pulsars are clocks, but they're also lighthouses, guides in the vastness of space. There are more planets than stars in the Milky Way. For most of history, we knew of only the planets in our own solar system. But in the past few decades, astronomers have discovered thousands of exoplanets, planets orbiting other stars. And the more we look, the more we find. Current estimates suggest there are more planets than stars in the Milky Way, possibly hundreds of billions. They come in all varieties. Gas giants larger than Jupiter, rocky worlds smaller than Earth, planets that orbit incredibly close to their stars, and others that drift in the cold outer regions. Some are in the habitable zone, the region where liquid water could exist on the surface. A few may even have conditions suitable for life. The sheer number is staggering. It means that almost every star you see likely has at least one planet. And among those billions, there are probably countless worlds as complex and fascinating as our own. Space telescopes can see farther than ground-based ones. Earth's atmosphere distorts light, creating the twinkling effect we see in stars. For astronomers, this is a problem because it blurs images and limits the detail we can observe. Space telescopes, like the Hubble and James Webb, orbit above the atmosphere, giving them a clear, unobstructed view of the universe. The James Webb Space Telescope, launched in 2021, is especially powerful. It observes in infrared wavelengths, allowing it to see through dust clouds and detect the faint heat of distant galaxies. It can peer back in time, observing galaxies that formed just a few 100 million years after the Big Bang. These telescopes have transformed our understanding of the universe, revealing details we could never see from the ground. They've shown us the birth of stars, the structure of distant galaxies, and the atmospheres of exoplanets. They remind us that to truly understand the cosmos, sometimes we need to leave Earth behind. The Sun will one day become a planetary nebula. When the Sun exhausts its hydrogen fuel in about 5 billion years, it will swell into a red giant, then begin to shed its outer layers. These layers will drift away, forming a glowing shell of gas called a planetary nebula. At the center will be the Sun's remaining core, a white dwarf, hot and slowly cooling. Planetary nebulae are some of the most beautiful objects in space. They glow in vibrant colors, reds, greens, blues, depending on the gases they contain and the energy from the central star. They come in many shapes: rings, spheres, butterflies, created by complex interactions of stellar winds and magnetic fields. Despite the name, they have nothing to do with planets. Early astronomers thought they looked similar to planets when viewed through small telescopes, and the name stuck. These nebulae don't last long, only a few tens of thousands of years before they fade and disperse. But in that brief window, they're a final, brilliant display, a star's last light before it settles into quiet darkness. The Great Attractor is pulling our galaxy. The Milky Way, along with thousands of other galaxies, is being pulled toward a region of space called the Great Attractor. This gravitational anomaly lies about 200 million light-years away, hidden behind the plane of our galaxy, making it difficult to observe directly. It's thought to be a massive concentration of mass, possibly a supercluster of galaxies or a region of dense dark matter. The Milky Way is moving toward it at about 600 kilometers per second, along with the rest of our local galactic neighborhood. What makes this even stranger is that the Great Attractor itself is being pulled toward an even larger structure, the Shapley supercluster. On the largest scales, the universe is a web of motion, with galaxies streaming along invisible rivers of gravity. We think of the Milky Way as stationary, but in reality, it's hurtling through space, carried by forces far beyond our control. There are planets where it rains glass. On a distant exoplanet called HD 189733b, the skies are a deep, vivid blue, but this isn't from oceans or clear air. It's from silicate particles in the atmosphere that scatter blue light. These particles condense into tiny droplets, creating clouds of molten glass. Winds on this planet reach up to 7,000 kilometers per hour, whipping these glass droplets sideways in a deadly storm. It quite literally rains glass, shards hurtling through the air at supersonic speeds. The planet orbits extremely close to its star, completing a full orbit in just 2.2 days. Temperatures soar to over 1,000 degrees Celsius. It's a world of extremes, beautiful from a distance but utterly hostile up close. This is just one example of how diverse exoplanets can be. Each new discovery expands our understanding of what's possible, showing us that the universe is far stranger and more varied than we ever imagined. Some stars are vampires. In close binary systems, where two stars orbit each other, one star can steal material from its companion. If one star is a white dwarf and the other is a larger, cooler star, the white dwarf's gravity can pull gas from the companion's outer layers. This material spirals around the white dwarf in an accretion disk, heating up and glowing brightly. Over time, hydrogen accumulates on the white dwarf's surface. When enough builds up, it can ignite in a sudden thermonuclear explosion, causing the star to brighten dramatically. This event is called a nova. Unlike a supernova, the star survives, and the process can repeat over and over. These vampire stars are fascinating examples of stellar evolution and interaction. They show that stars aren't always solitary, stable objects. They can have complex, dynamic relationships that dramatically alter their fates. The Hubble Deep Field revealed thousands of galaxies. In 1995, astronomers pointed the Hubble Space Telescope at a tiny, seemingly empty patch of sky, no bigger than a grain of sand held at arm's length. They left the telescope focused on that spot for 10 days, collecting light from the faintest, most distant objects. When the image was revealed, it stunned the world. The empty patch contained over 3,000 galaxies, each one a collection of billions of stars, some shaped like spirals, others irregular or elliptical. Many were so far away that their light had traveled for billions of years. This single image transformed our understanding of the universe's scale. It showed that no matter where we look, even in the darkest corners of the sky, the cosmos is filled with galaxies. Since then, even deeper observations have been made, revealing galaxies from when the universe was less than 1 billion years old. The Hubble Deep Field is a reminder that the universe is vast beyond comprehension, and every point in the sky holds wonders. The International Space Station orbits Earth every 90 minutes, traveling at about 28,000 kilometers per hour. The ISS completes an orbit roughly every hour and a half. This means astronauts aboard experience 16 sunrises and sunsets every day. The station orbits at an altitude of about 400 kilometers, just high enough to avoid significant atmospheric drag, but low enough to be reached by spacecraft from Earth. It's a marvel of engineering, assembled piece by piece in orbit over more than a decade. Astronauts from around the world live and work aboard, conducting experiments in microgravity, studying Earth from space, and testing technologies for future missions. From the ground, the ISS is visible to the naked eye, appearing as a bright, fast-moving point of light crossing the sky. It's one of the few human-made objects you can see without a telescope. Watching it pass is a reminder that humans are explorers, building outposts beyond our world. Light pollution hides the stars from most of humanity. For most of human history, the night sky was a source of wonder, a tapestry of stars visible to anyone who looked up. But today, more than 80% of the world's population lives under light-polluted skies. In cities, artificial light drowns out all but the brightest stars. The Milky Way, once a common sight, is now invisible to billions of people. This loss isn't just aesthetic. It affects wildlife, disrupts ecosystems, and disconnects us from the cosmos. Many animals rely on natural darkness for navigation, hunting, and reproduction. Excessive light at night can confuse migratory birds, disorient sea turtles, and disrupt insect populations. For humans, losing the night sky means losing a connection to something ancient and profound. But the solution is simple. Shielding lights, using dimmer bulbs, and turning off unnecessary illumination can bring back the stars. In dark sky reserves and remote areas, the night sky still reveals its full glory. And for those who've never seen it, the experience is unforgettable. Some galaxies are so distant their light will never reach us. The universe is expanding, and the farther away a galaxy is, the faster it's receding. Beyond a certain distance, galaxies are moving away from us faster than the speed of light, not because they're traveling through space at that speed, but because space itself is expanding. Light from these galaxies will never reach us. No matter how long we wait, we'll never see them. This boundary is called the cosmic horizon. As time passes, more and more galaxies will cross this horizon and disappear from view. In the far future, trillions of years from now, only the galaxies in our local group will remain visible. The rest of the universe will have receded beyond reach. This means the universe we observe is just a fraction of what exists. There are entire regions, entire galaxies, that we'll never know about. It's a humbling thought. A reminder that even with all our technology, there are limits to what we can see. The oldest stars are almost as old as the universe. The universe is about 13.8 billion years old. Some of the oldest known stars, found in ancient globular clusters, are over 13 billion years old. They formed in the first few 100 million years after the Big Bang, when the universe was still young and filled mostly with hydrogen and helium. These stars contain almost no heavy elements, a sign that they formed before many generations of supernovae had enriched the cosmos with metals. Studying these ancient stars gives us a glimpse into the early universe, a time when galaxies were just beginning to form and the first light was breaking through the cosmic dark. They're like fossils, preserving information about conditions we can't observe any other way. And they remind us that some things in the universe are incredibly old, far older than Earth, older than our sun, older than anything in our solar system. Space is expanding, but galaxies aren't. While the universe as a whole is expanding, individual galaxies are not. They're held together by gravity, which is much stronger on small scales than the expansion of space. The same is true for solar systems, planets, and even atoms. The expansion only becomes noticeable over vast distances between galaxy clusters and superclusters. On these scales, space is stretching, carrying galaxies apart. But within a galaxy, or even within a cluster, gravity keeps things bound. This is why the Milky Way and Andromeda are moving toward each other, not away. Gravity overcomes the expansion. It's a balance of forces, expansion pushing outward, gravity pulling inward. On human scales, we don't notice either, but on cosmic scales, they shape the structure of the universe. The Voyager spacecraft have left the solar system. Launched in 1977, Voyager 1 and Voyager 2 are the most distant human-made objects. Both have crossed the heliopause, the boundary where the solar wind gives way to interstellar space. They're now traveling through a region influenced more by other stars than by our sun. Voyager 1 is over 23 billion kilometers from Earth, and its signals take more than 20 hours to reach us. Both spacecraft still send back data powered by slowly decaying plutonium generators. They'll continue operating for a few more years before their power runs out. After that, they'll drift silently through the galaxy for billions of years. Each carries a golden record, a time capsule containing sounds, music, and images from Earth, a message to any civilization that might one day find them. The Voyagers are ambassadors, not just to space, but to the future. There are more galaxies in the universe than we can count. Current estimates suggest there are at least 200 billion galaxies in the observable universe, but that's likely an underestimate. Some are too faint, too far, or hidden behind dust. The true number could be much higher. Each galaxy contains billions or even trillions of stars, and each star could have planets. The scale is almost impossible to grasp. If you counted one galaxy every second, it would take over 6,000 years to count them all. And that's just the observable universe. The true size, if the universe is infinite, could contain an infinite number of galaxies. We live in just one, orbiting just one star, on just one planet. It's a humbling perspective, but also a beautiful one. We're part of something vast, connected to a cosmos that stretches beyond imagination. Black holes can evaporate. According to Stephen Hawking, black holes aren't entirely black. They emit a faint radiation, now called Hawking radiation, due to quantum effects near the event horizon. Over incredibly long timescales, this radiation causes black holes to lose mass and eventually evaporate. For stellar mass black holes, this process takes longer than the current age of the universe. But for tiny primordial black holes, it could happen much faster. As a black hole shrinks, it radiates faster, eventually exploding in a burst of energy. No one has ever observed this, but the theory is well established. It's a strange idea that something as absolute as a black hole can slowly fade away. But it's consistent with the laws of quantum mechanics and thermodynamics. In the far future, after all the stars have died and the galaxies have faded, black holes will be among the last objects in the universe, and even they will eventually disappear. Astronauts grow taller in space. In the microgravity of space, the spine is no longer compressed by the weight of the body. The discs between vertebrae expand slightly, causing astronauts to grow up to 5 centimeters taller. This can cause back pain and discomfort as muscles and ligaments adjust. When they return to Earth, gravity compresses the spine again, and they return to their normal height. Other changes happen too. Without gravity, fluids shift toward the upper body, causing facial puffiness and congestion. Muscles and bones weaken without the resistance of weight bearing. Astronauts must exercise for hours each day to counteract these effects. The human body is adapted for life on Earth, and space presents challenges we're still learning to manage. But each mission teaches us more, bringing us closer to the day when humans might live and work in space for extended periods. Some stars pulse like cosmic heartbeats. Variable stars change in brightness over time, sometimes in regular, predictable patterns. Cepheid variables, for example, expand and contract rhythmically, growing brighter and dimmer in cycles that can last days or weeks. The period of these pulsations is directly related to the star's intrinsic brightness, making them incredibly useful for measuring distances across the universe. Astronomers use them as standard candles, cosmic rulers that help map the scale of galaxies and the expansion of space. Other variable stars pulse more erratically, driven by instabilities in their outer layers or by interactions with companion stars. Watching their light curves is like listening to the rhythm of the cosmos, each pulse a beat in the great symphony of stellar life. There may be parallel universes. Some interpretations of quantum mechanics and cosmic inflation suggest that our universe might be just one of many, possibly infinite, parallel universes. In these other universes, the laws of physics might be different. Fundamental constants, like the strength of gravity or the charge of an electron, could have different values. Some universes might be lifeless. Others might be filled with exotic forms of matter we can't imagine. This idea, known as the multiverse, is speculative and untestable with current technology, but it arises naturally from certain theories. If it's true, It would mean that everything we observe, all the galaxies, stars, and planets, is just a tiny fraction of existence. It's a concept that stretches the imagination to its limits, blurring the line between science and philosophy. The universe might be shaped like a donut. The shape of the universe is one of the great unanswered questions in cosmology. Current observations suggest it's flat, meaning parallel lines will remain parallel forever. But there's another possibility. The universe could be finite but unbounded, shaped like a torus or donut. In this model, if you traveled far enough in one direction, you'd eventually return to your starting point, like a spaceship in an old video game wrapping around the screen. Light could also wrap around, meaning we might be seeing the same galaxies multiple times from different directions. So far, there's no evidence for this. The universe appears to be flat on all scales we can observe, but we can only see a tiny fraction of it. The true shape remains a mystery. Stars twinkle, but planets don't. When you look at the night sky, stars appear to twinkle, flickering and changing brightness. This isn't because the stars themselves are changing. It's because their light passes through Earth's turbulent atmosphere, which bends and distorts the light in random ways. Planets, on the other hand, appear as small disks rather than points of light, even if they're too small to resolve with the naked eye. This means their light is less affected by atmospheric turbulence, and they shine steadily. Ancient astronomers used this difference to distinguish planets from stars long before telescopes were invented. It's a subtle clue, but one that reveals the fundamental difference between nearby worlds and distant suns. Gravity is the weakest fundamental force. There are 4 fundamental forces in nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity is by far the weakest. A small magnet can easily overcome the gravitational pull of the entire Earth. So why does gravity dominate on cosmic scales? Because it has infinite range and only attracts, never repels. Mass attracts more mass, and over vast distances, gravity shapes the structure of galaxies, clusters, and the universe itself. On small scales, quantum forces dominate, but on the largest scales, gravity is king. It bends light, warps space, and determines the fate of the cosmos. The speed of light is not just about light. The speed of light, about 300,000 kilometers per second, is actually the speed of causality, the maximum speed at which information can travel. Light happens to travel at this speed because photons have no mass. But the limit applies to everything. No matter, no energy, no information can move faster. It's woven into the structure of space and time. This limit has profound implications. It means distant events can't affect us instantly. It means the universe has a horizon beyond which we can't see. And it means time travel, at least to the past, is almost certainly impossible. The speed of light is a fundamental constant, one of the numbers that defines our universe. And so, our journey through the stars draws to a close. We've wandered among planets and galaxies, through the hearts of stars and the edges of the cosmos. Each fact, each revelation has been a small candle in the vast darkness, a reminder that even in the quietest hours, the universe hums with wonder and mystery. Perhaps some of these truths have stayed with you, or perhaps they've already drifted away as you floated further into rest. That's the beauty of a night spent among the stars. You don't need to hold on to every detail. The universe will still be there tomorrow, waiting for you, vast and patient. If you happen to still be awake, you can go ahead and watch another video. But if your eyes are heavy and your thoughts are soft, you can simply let yourself drift, carried by the gentle pull of sleep. wrapped in the quiet knowledge that you're part of something infinite. Sleep well, and good night. The Sun is 1,000,000 times larger than Earth in volume. It's easy to forget how massive the Sun truly is. If it were hollow, you could fit about 1.3 million Earths inside it. Its diameter is about 1.4 million kilometers, roughly 109 times that of Earth. Despite this enormous size, the Sun is actually a fairly average star. Some stars are hundreds of times larger. But from our perspective, the Sun is everything. It provides the light and warmth that makes life possible. It holds the entire solar system in its gravitational embrace, keeping planets, asteroids, and comets in their orbits. The Sun contains 99.8% of all the mass in the solar system. Everything else, all the planets, moons, asteroids, and comets combined, makes up just a tiny fraction. We live in a solar system dominated by a single object, a glowing sphere of hydrogen and helium that has been burning for 4.5 billion years and will continue for billions more. There are clouds in space made of alcohol and sugar. In a giant molecular cloud near the center of the Milky Way, astronomers have detected vast quantities of ethanol, the same type of alcohol found in beverages, and glycolaldehyde, a simple sugar molecule. This cloud, called Sagittarius B2, contains enough ethanol to fill trillions upon trillions of bottles. Of course, it's mixed with other chemicals and is utterly undrinkable. But its presence reveals something important. Complex organic molecules can form naturally in space. These molecules are created on the surfaces of dust grains, where atoms stick together in the cold, forming chains and rings. They're then released into space by radiation or heat. Finding alcohol and sugar in space doesn't mean there's a cosmic bar, but it does mean that the chemistry of life, the building blocks of organic compounds, can form in the most unexpected places. Venus rotates backwards compared to most planets. If you could stand on Venus and watch the sun rise, you'd see it appear in the west and set in the east. That's because Venus rotates in the opposite direction to most other planets in the solar system. This retrograde rotation is likely the result of a massive collision early in its history, an impact so powerful it flipped the planet's spin. But that's not the only strange thing about Venus's rotation. It also rotates incredibly slowly. A single day on Venus, one full rotation, takes 243 Earth days, but its year, one orbit around the Sun, takes only 225 Earth days. This means a day on Venus is longer than its year. Combined with its thick, toxic atmosphere and surface temperatures hot enough to melt lead, Venus is one of the most hostile and unusual worlds in the solar system. Galaxies have different shapes for different reasons. Galaxies come in a variety of shapes, and each tells a story about its history. Spiral galaxies like the Milky Way have arms of stars, gas, and dust winding outward from a central bulge. These arms are regions of active star formation, where new stars are being born. Elliptical galaxies are smooth and featureless, often formed through the merger of two or more spiral galaxies. They contain older stars and little gas, so they're not forming many new stars. Then there are irregular galaxies, which have no clear shape at all. These are often the result of gravitational interactions or collisions. The shape of a galaxy depends on its history, its rotation, and the gravitational forces acting on it. Studying galaxy shapes helps astronomers understand how galaxies form, evolve, and interact over billions of years. The surface of the Sun is constantly boiling. The Sun's surface is not solid. It's a churning sea of plasma, gas so hot that electrons are stripped from atoms. This plasma rises and falls in convection cells, similar to boiling water in a pot. Hot plasma rises to the surface, cools slightly, then sinks back down to be reheated. This creates a granulated texture, like grains of rice, each one about 1,000 kilometers across. These granules appear and disappear in just minutes, a constant, dynamic motion. Above the surface, the sun's atmosphere is even more active, with solar flares and coronal mass ejections that send bursts of charged particles streaming into space. The sun is not a calm, steady object. It's a violent, energetic ball of plasma, constantly roiling and erupting. And yet, from Earth, it appears as a serene, unchanging disk of light. Some asteroids have their own moons. Asteroids are usually thought of as solitary rocks tumbling through space, but many asteroids have small companions, tiny moons orbiting them. These moonlets are captured fragments from collisions or pieces of the asteroid itself that broke off and remained in orbit. Some asteroid systems are binary, with two similarly sized objects orbiting each other. The asteroid Didymos and its moon Dimorphos became famous in 2022 when NASA deliberately crashed a spacecraft into Dimorphos to test asteroid deflection technology. The impact successfully changed the moon's orbit, proving that we have the ability to alter the path of an asteroid if one threatens Earth. These small moons reveal that even asteroids can have complex gravitational relationships, and studying them helps us understand the dynamics of the early solar system. The Oort cloud surrounds our solar system like a shell. Far beyond the orbit of Neptune, beyond the Kuiper belt where Pluto resides, lies the Oort cloud, a vast spherical shell of icy objects surrounding the entire solar system. It extends from about 2,000 to 100,000 astronomical units from the Sun, nearly halfway to the nearest star. The Oort cloud is thought to contain trillions of comets, remnants from the formation of the solar system, ejected to these distant reaches by the gravity of the giant planets. Occasionally, a passing star or gravitational disturbance nudges one of these objects inward, sending it on a journey toward the Sun. These long-period comets can take thousands or even millions of years to complete a single orbit. The Oort cloud has never been directly observed. It's too far and too faint, but its existence is inferred from the orbits of comets that occasionally visit the inner solar system. Earth's magnetic field protects us from solar wind. The Sun constantly emits a stream of charged particles called the solar wind. If this wind reached Earth's surface unimpeded, it would strip away our atmosphere and make life impossible. But Earth has a shield, its magnetic field, generated by the motion of molten iron in the planet's core. This field extends far into space, deflecting most of the solar wind around the planet. When particles do penetrate near the poles, they interact with the atmosphere, creating the auroras, the northern and southern lights. Without this magnetic shield, Earth would look very different. Mars, for example, lost its magnetic field billions of years ago. Over time, the solar wind stripped away much of its atmosphere, leaving it cold, dry, and barren. Earth's magnetic field is one of the key factors that makes our planet habitable. It's invisible, but it's constantly protecting us. Titan has lakes of liquid methane. Saturn's largest moon, Titan, is the only place in the solar system besides Earth known to have stable liquid on its surface. But instead of water, Titan's lakes and seas are filled with liquid methane and ethane. Its thick atmosphere, denser than Earth's, is composed mostly of nitrogen with traces of methane. Temperatures are so cold, around minus 179 degrees Celsius, that methane behaves like water, evaporating, forming clouds, and falling as rain. Titan has a weather cycle similar to Earth's water cycle. But with methane, there are rivers, lakes, and even seas, some larger than the Great Lakes. Beneath the surface, scientists believe there may also be a subsurface ocean of liquid water kept from freezing by tidal heating. Titan is one of the most Earth-like worlds we've discovered, even though its surface conditions are utterly alien. Supermassive black holes lurk at the centers of most galaxies. At the heart of the Milky Way, about 26,000 light-years from Earth, lies a supermassive black hole called Sagittarius A star. It has a mass about 4 million times that of the Sun. This isn't unique. Most large galaxies have supermassive black holes at their centers, some with masses of billions of suns. These black holes likely formed in the early universe, growing over billions of years by devouring gas, dust, and stars. They shape the evolution of their host galaxies, regulating star formation through powerful jets and winds. When actively feeding, they become quasars, some of the brightest objects in the universe. Despite their name, supermassive black holes are not giant vacuum cleaners. Objects must get very close to be pulled in. The Sun, for example, orbits Sagittarius A star at a safe distance and will continue to do so for billions of years. There are more atoms in a glass of water than stars in the universe. It's a staggering comparison. A single glass of water contains roughly 10 to the power of 24 atoms. The observable universe contains about 200 billion trillion stars, or 2 times 10 to the power of 23. That means a glass of water has about 5 times more atoms than there are stars in the universe. This comparison highlights just how small atoms are and how vast numbers can become when you're dealing with matter. Every breath you take contains trillions upon trillions of atoms, and yet those atoms are almost entirely empty space. If you could remove all the empty space from the atoms in your body, you'd be smaller than a grain of dust. Matter is mostly void, held together by forces we can't see. It's a strange and beautiful truth about the nature of reality. Mercury has ice despite being the closest planet to the Sun. It seems contradictory. Mercury orbits closer to the Sun than any other planet, with surface temperatures soaring to over 400 degrees Celsius during the day. But in permanently shadowed craters near its poles, temperatures drop to minus 170 degrees Celsius, cold enough to preserve water ice. Radar observations and data from spacecraft have confirmed the presence of this ice, likely delivered by comets or asteroids billions of years ago. The ice has remained frozen in these dark craters, untouched by sunlight, for eons. It's a reminder that even in extreme environments, conditions can vary dramatically. On Mercury, you could have scorching heat just a few meters from frozen water. The solar system is full of such contrasts. Some exoplanets orbit their stars in just a few hours. Hot Jupiters are gas giants that orbit incredibly close to their stars, sometimes completing an orbit in less than a day. One exoplanet, WASP 1-2b, has an orbital period of just over 26 hours. At this distance, the planet is so close to its star that it's being torn apart by tidal forces. Its atmosphere is being stripped away, forming a glowing halo around the planet. These worlds are tidally locked, with one side in permanent daylight and the other in endless night. Temperatures on the day side can exceed 2,000 degrees Celsius, hot enough to vaporize metals. These planets likely formed farther out and migrated inward over time. They're extreme environments, utterly unlike anything in our solar system. Our solar system is moving through the Milky Way. The Sun, along with all the planets, is orbiting the center of the Milky Way at a speed of about 800,000 kilometers per hour. It takes roughly 230 million years to complete one orbit, a period sometimes called a galactic year. The last time the Sun was in this position, dinosaurs hadn't yet appeared on Earth. This motion is part of a larger pattern. The entire Milky Way is moving through space, pulled toward the Great Attractor and the Shapley supercluster. On the largest scales, everything is in motion. There is no fixed point in the universe. Everything is drifting, orbiting, falling, carried by gravity's invisible currents. The universe is mostly empty space. Despite containing billions of galaxies, each with billions of stars, the universe is mostly empty. The distances between stars are vast. Even within a galaxy, the space between stars is enormous. If the sun were the size of a grain of sand, the nearest star would be about 10 kilometers away. On larger scales, galaxies are separated by millions of light years of near empty space. And the space between galaxy clusters is even more barren. If you could shrink the universe down, it would resemble a foam. With galaxies clustered along thin filaments and walls, surrounding vast voids where almost nothing exists. The universe is more emptiness than substance, and yet that emptiness is not truly empty. It's filled with dark matter, dark energy, and the faint afterglow of the Big Bang. The asteroid belt is not densely packed. In movies and video games, the asteroid belt is often depicted as a chaotic field of rocks that spacecraft must navigate carefully. But in reality, the asteroid belt is mostly empty space. The asteroids are spread out over such a vast area that you could pass through it and likely never see a single one with the naked eye. Spacecraft routinely travel through the asteroid belt without incident. The total mass of all asteroids combined is less than that of our moon. Most of this mass is concentrated in just a few large objects, like Ceres, which is classified as a dwarf planet. The asteroid belt is a relic from the early solar system, material that never coalesced into a planet due to Jupiter's gravitational influence. It's a ring of rubble, spread thin across millions of kilometers. Pulsars help prove the existence of planets beyond our solar system. Before the 1,990 seconds, we had no confirmed evidence of planets orbiting other stars. The first exoplanets ever discovered weren't found around a normal star, but around a pulsar, a rapidly rotating neutron star. Pulsars emit regular pulses of radiation with extraordinary precision. Astronomers noticed tiny variations in the timing of these pulses from the pulsar PSR B1257 plus 12. These variations indicated the gravitational tug of planets orbiting the pulsar. It was an unexpected discovery. Pulsars are the remnants of supernova explosions, and the planets likely formed from the debris. They're exposed to intense radiation and would be utterly inhospitable to life. But their discovery was groundbreaking, proving that planets can exist in the most extreme environments. Since then, thousands of exoplanets have been discovered around normal stars. The light from stars tells us what they're made of. When light passes through a gas, certain wavelengths are absorbed, creating dark lines in the spectrum. By analyzing these lines, astronomers can determine the chemical composition of a star, even from billions of light years away. Every element absorbs light at specific wavelengths, creating a unique fingerprint. This technique, called spectroscopy, has revealed that stars are made mostly of hydrogen and helium, with traces of heavier elements. It's also allowed us to measure the temperatures, velocities, and magnetic fields of stars. Spectroscopy is one of the most powerful tools in astronomy. It turns light into information, allowing us to study objects we'll never visit. We can know what a distant star is made of with greater certainty than we know the composition of Earth's core. Some stars are born in pairs. About half of all stars in the Milky Way are part of binary or multiple star systems. They orbit each other, bound by gravity, sometimes so close they share material. In some cases, one star can strip gas from its companion, feeding on it like a cosmic vampire. In others, the stars are widely separated, orbiting each other over thousands or millions of years. Binary stars can create spectacular phenomena. If one star goes supernova, it can blow its companion away at high speed, creating a runaway star. If both stars are massive, they can eventually merge, forming a single, larger star or collapsing into a black hole. Studying binary stars helps us understand stellar evolution, mass transfer, and the dynamics of close gravitational systems. They remind us that stars, like people, are often not alone. The largest known structure in the universe is a supercluster. The Hercules Corona Borealis Great Wall is a massive structure of galaxies stretching over 10 billion light-years across. It's so large that light takes about 10 billion years to travel from one end to the other. Structures like this challenge our understanding of how the universe formed. According to some models, the universe shouldn't have had enough time to create such massive structures. Their existence suggests that our understanding of cosmic evolution may still be incomplete. These superclusters are part of the cosmic web, the large-scale structure of the universe where galaxies cluster along filaments of dark matter. They're the largest known patterns in existence, and they hint at the processes that shape the universe over billions of years. The Milky Way will collide with Andromeda in about 4 billion years. The Andromeda Galaxy, our nearest large neighbor, is currently about 2.5 million light-years away, but it's moving toward us at about 110 kilometers per second. In roughly 4 billion years, the two galaxies will begin to merge. This won't be a sudden crash. The collision will unfold over hundreds of millions of years, with the galaxies passing through each other, their shapes distorting, before eventually settling into a single, larger elliptical galaxy. From Earth, if anyone is around to see it, the night sky will be transformed. Andromeda will grow larger and larger, eventually dominating the view. New stars will ignite in bursts of formation. The skies will be filled with light. Our sun will likely survive, though it may be flung into a new orbit. It's a reminder that even galaxies have life cycles, and change is inevitable, even on cosmic scales. There are more possible games of chess than atoms in the observable universe. This is a fun comparison. A number of possible unique chess games is estimated to be around 10 to the power of 120, a number so large it's called the Shannon number. The observable universe contains about 10 to the power of 80 atoms. This means there are far more possible chess games than there are atoms in existence. It's a testament to the complexity that can arise from simple rules. With just 64 squares and a handful of pieces, chess contains near infinite variety. In a similar way, the laws of physics, relatively simple at their core, give rise to the immense complexity and beauty of the universe. The asteroid that killed the dinosaurs left a massive crater. 66 million years ago, an asteroid about 10 kilometers wide struck Earth near the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of atomic bombs, creating a crater over 150 kilometers wide. The asteroid vaporized on impact, sending a plume of debris into the atmosphere that spread around the globe. Wildfires ignited across continents, tsunamis hundreds of meters high swept over coastlines, and the sky filled with dust and ash, blocking out the sun for years. This triggered a mass extinction event that wiped out about 75% of all species on Earth, including the non-avian dinosaurs. The crater, now called the Chicxulub crater, is buried beneath sediment but has been mapped using gravity and magnetic surveys. It's a scar from one of Earth's most catastrophic events, a reminder that space can be dangerous. You can see 5 planets with the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn are all visible without a telescope. Ancient astronomers knew these planets well, tracking their movements across the sky. They called them wanderers because unlike the stars, which seemed fixed, these objects moved. Venus is often the brightest object in the night sky after the moon, shining brilliantly in the early morning or evening. Jupiter, with its massive size, is also very bright. Mars is recognizable by its reddish color. Mercury is harder to spot because it's always close to the sun, visible only near the horizon at dawn or dusk. Saturn is dimmer but still visible to patient observers. With a good pair of binoculars, you can even see Jupiter's 4 largest moons and Saturn's rings. The night sky offers a connection to the cosmos that doesn't require expensive equipment, just patience and curiosity. There are diamonds in the cores of some planets. Inside gas giants like Neptune and Uranus, the pressure and temperature are so intense that carbon atoms can be squeezed into diamond crystals. Scientists have recreated these conditions in laboratories using powerful lasers to compress hydrocarbons into tiny diamonds. These diamonds likely form deep in the planet's atmospheres and then rain down through the layers of gas, accumulating in massive deposits in the core. It's a beautiful and strange thought, an ocean of liquid diamond deep inside a distant world. We'll never be able to mine these treasures, but knowing they exist makes these planets seem even more wondrous. The sun will eventually engulf Earth. In about 5 billion years, the sun will exhaust the hydrogen in its core and begin fusing hydrogen in a shell around the core. This will cause the sun to expand into a red giant, its outer layers swelling to perhaps 100 times its current size. At this size, the sun will likely engulf Mercury and Venus. Earth's fate is uncertain. Some models suggest it will be swallowed as well. Others predict that as the sun loses mass, Earth's orbit will expand just enough to avoid being consumed. But even if Earth survives, it won't be habitable. The sun's heat will boil away the oceans and scorch the surface. Long before this happens, life on Earth will have ended. The sun's increasing luminosity will make the planet too hot for liquid water in about 1 billion years. These are distant events, but they're inevitable. Quasars are the brightest objects in the universe. Quasars are supermassive black holes at the centers of distant galaxies, actively feeding on vast amounts of gas and dust. As material spirals into the black hole, it heats to millions of degrees, emitting enormous amounts of light across the electromagnetic spectrum. A single quasar can outshine an entire galaxy of hundreds of billions of stars. They're so bright that we can see them from billions of light years away, making them some of the most distant objects we've ever observed. Quasars were most common in the early universe, when galaxies were young and had more material to feed their central black holes. Today, they're rarer. Our own galaxy's supermassive black hole is relatively quiet, feeding only occasionally. But in the distant past, it may have been a quasar, blazing with light. The fastest winds in the solar system are on Neptune. Neptune, the farthest planet from the Sun, has winds that reach speeds of over 2,000 kilometers per hour, the fastest ever recorded in the solar system. These supersonic winds scream through Neptune's upper atmosphere, driving massive storm systems. The Great Dark Spot, a storm similar to Jupiter's Great Red Spot, was observed by Voyager 2 inches 1,989. By the time Hubble looked at Neptune in 1994, the storm had disappeared, replaced by new storms in other regions. Neptune's extreme weather is puzzling because the planet is so far from the Sun and receives very little solar energy. The winds are likely powered by heat from Neptune's interior, left over from its formation. It's a reminder that even cold, distant worlds can be dynamic and active. The speed of light defines our cosmic horizon. Because the universe is expanding and light has a finite speed, there's a limit to how far we can see. The observable universe has a radius of about 46 billion light-years. Beyond that distance, light hasn't had enough time to reach us since the Big Bang. This creates a cosmic horizon, a boundary beyond which we cannot see. As time passes, more light will arrive, and the observable universe will grow. But because the expansion is accelerating, some galaxies will eventually move beyond our horizon and disappear from view forever. In the far future, trillions of years from now, only the galaxies in our local group will remain visible. The rest of the universe will have receded beyond reach. It's a reminder that what we see is not all that exists. The universe is larger, perhaps infinitely so, than we can ever observe. Earth has had 5 major mass extinction events. Over the past 500 million years, Earth has experienced 5 major extinction events where a significant percentage of life was wiped out. The most famous is the one that killed the dinosaurs 66 million years ago, but there were others. The Permian-Triassic extinction, about 250 million years ago, was the worst, killing over 90% of all species. These events were caused by a variety of factors: asteroid impacts, massive volcanic eruptions, climate change, and shifts in ocean chemistry. Each time, life recovered, evolving new forms to fill the empty niches. Some scientists believe we're currently in the midst of a 6th mass extinction driven by human activity. Habitat destruction, climate change, and pollution are causing species to disappear at rates not seen since the dinosaurs. But as history shows, life is resilient. It endures, adapts, and finds a way to continue. Space smells like burnt metal and seared steak. Astronauts who've performed spacewalks report a distinct smell when they return to the spacecraft and remove their helmets. They describe it as a metallic, burnt odor, similar to welding fumes or seared meat. This smell doesn't come from space itself, which is a vacuum. Instead, it's likely caused by high-energy particles, cosmic rays, and solar wind that cling to the spacesuit. When exposed to the oxygen-rich environment of the spacecraft, these particles react, creating the unusual smell. It's one of those small, unexpected details that make space exploration feel more real and tangible. Space isn't just something we see through telescopes. It's something that can be smelled, felt, and experienced directly. Some ancient cultures predicted eclipses with remarkable accuracy. Long before modern astronomy, ancient civilizations like the Babylonians and the Maya developed systems to predict solar and lunar eclipses. They didn't understand the mechanics, the interplay of the sun, earth, and moon, but they recognized patterns. Eclipses occur in cycles, repeating at regular intervals. The Saros cycle, for example, is about 18 years. By tracking eclipses over centuries, ancient astronomers could predict when the next one would occur. These predictions were often tied to religious or political events, adding weight to the power of priests and rulers. It's a testament to human curiosity and ingenuity. Even without technology, we found ways to make sense of the cosmos. The moon causes tides on Earth. Twice a day, the oceans rise and fall in a rhythm dictated by the moon's gravity. As the moon orbits Earth, its gravitational pull creates a bulge of water on the side facing the moon and another on the opposite side. As Earth rotates beneath these bulges, different locations experience high and low tides. The sun also affects tides, though to a lesser extent. When the sun, Earth, and moon align during a full or new moon, their gravitational pulls combine, creating spring tides, which are higher than usual. When they're at right angles during a quarter moon, their pulls partially cancel out, creating neap tides, which are lower. Tides have shaped life on Earth for billions of years. They influence migration, feeding patterns, and ecosystems. They're a constant reminder of the moon's presence, a pull we feel every day. Some stars are older than the universe. Wait, that can't be right. But for a time, it seemed to be true. In the 1,990 seconds, astronomers measured the ages of certain globular cluster stars and found them to be older than the estimated age of the universe. This created a paradox. How could something be older than everything? The resolution came from better measurements, improved observations of the cosmic microwave background, and distant supernovae refined the age of the universe to about 13.8 billion years. Meanwhile, better measurements of stellar ages brought the oldest stars to about 13 billion years. The paradox was resolved, but for a while it was a genuine mystery, a reminder that our understanding of the cosmos is always evolving, always being refined. The great red spot on Jupiter is shrinking. For centuries, the great red spot has been a defining feature of Jupiter, a massive storm large enough to swallow multiple Earths. But in recent decades, it's been getting smaller. Observations from the 1800s suggest it was once over 40,000 kilometers wide. Today, it's less than half that size. No one knows why it's shrinking. It could be a natural cycle, or it could be a sign that the storm is finally dying. Some scientists believe it will disappear within a few decades. Others think it will stabilize. Jupiter's atmosphere is complex, and we're still learning how its storms form and evolve. Whether the Great Red Spot will vanish or endure remains one of the planet's great mysteries. Our sun is about halfway through its life. The sun formed about 4.5 billion years ago and has enough hydrogen fuel to continue fusing for another 5 billion years. That puts it roughly at the midpoint of its life. For now, it's a stable, middle-aged star, steadily converting hydrogen into helium in its core. Over time, it will grow slightly hotter and brighter. In about 1 billion years, this increased luminosity will make Earth too hot for liquid water. Eventually, the sun will exhaust its hydrogen and expand into a red giant. But for now, it's steady, reliable, and life-sustaining. We live in the sun's most stable phase, a fortunate time for the existence of life. And so, our journey through the cosmos draws to a close. We've traveled from the smallest atoms to the largest structures, from the birth of stars to the fate of galaxies. Each truth, each wonder, has been a gentle light in the vast expanse, a reminder that even in stillness, the universe is alive with beauty and mystery. Perhaps some of these stories have lingered with you, or perhaps they've drifted away like stars fading into dawn. That's perfectly fine. The universe will still be there tomorrow, patient and endless, waiting for you to look up once more. If you're still awake, you're welcome to explore more journeys. But if your thoughts are soft and your breathing slow, simply let yourself rest. Let the quiet pull of sleep carry you gently. You're a part of this vast cosmos, connected to the stars, the planets, and the endless dance of time. Sleep well, traveler, and good night. The International Space Station travels at 17,500 miles per hour. That's about 5 miles per second, fast enough to circle the entire Earth in just 90 minutes. At this speed, astronauts aboard the ISS experience 16 sunrises and sunsets every day. They watch the sun climb above Earth's horizon, blaze across the sky, and disappear again in less than an hour. The speed is necessary to maintain orbit. Any slower and gravity would pull the station down. Any faster and it would escape into space. It's a delicate balance, constantly maintained by occasional thruster burns and orbital adjustments. Despite this incredible speed, astronauts inside experience weightlessness. They float freely, unaware of their motion except for the view outside, watching Earth spin beneath them in a silent dance. There's a planet made entirely of water, GJ 1214. B is an exoplanet, about 40 light years from Earth. It's classified as a water world, believed to be covered entirely by a global ocean hundreds of kilometers deep. Unlike Earth's oceans, which rest on a rocky crust, this planet's water extends all the way down. At the bottom, the pressure is so immense that water is compressed into exotic forms, like Ice 7 or Ice X, solid phases of water that form under extreme pressure despite high temperatures. The surface, if it can be called that, might be covered in a thick, steamy atmosphere. No dry land, no continents, just water and sky. It's a world utterly unlike anything in our solar system, and it challenges our ideas about what planets can be. Io is the most volcanically active body in the solar system. Jupiter's moon Io is constantly erupting, its surface covered with hundreds of active volcanoes. Plumes of sulfur and sulfur dioxide shoot hundreds of kilometers into space. Lava flows reshape the surface so quickly that impact craters barely have time to form before being covered over. The source of this activity is tidal heating. Io orbits Jupiter in a slightly elliptical path, and the planet's immense gravity squeezes and stretches the moon as it moves closer and farther. This friction generates heat, enough to keep Io's interior molten. The result is a world painted in yellows, reds, and blacks, a surface that glows with lava and erupts with violent regularity. It's one of the most extreme and dynamic places in the solar system. Pluto has a heart-shaped glacier. When NASA's New Horizons spacecraft flew past Pluto in 2015, it revealed a world far more complex and beautiful than anyone expected. One of the most striking features is Tombaugh Regio, a bright, heart-shaped region on Pluto's surface. The left lobe of the heart, Sputnik Planitia, is a massive glacier made of nitrogen ice. It's over 1,000 kilometers wide and fills an ancient impact basin. The nitrogen ice is constantly churning in convection cells, slowly renewing the surface and erasing craters. Around the edges, nitrogen ice sublimates during Pluto's summer and refreezes during its winter, creating seasonal changes. Pluto may be small and distant, but it's geologically active and visually stunning. It's a reminder that even in the cold outer reaches of the solar system, there's beauty and complexity. Stars form in clusters, then drift apart. When stars are born, they're often born in groups, clustered together in stellar nurseries. These open clusters can contain dozens, hundreds, or even thousands of stars, all formed from the same cloud of gas and dust. Over time, gravitational interactions and the motion of the galaxy cause the cluster to disperse. Stars drift apart, spreading out across the galaxy. The Sun was likely born in such a cluster about 4.5 billion years ago. Its siblings, stars formed from the same cloud, are now scattered across the galaxy, impossible to identify. But somewhere out there are stars that share the Sun's origin. Distant relatives will never meet. It's a poetic thought that the Sun has family, even if we can't find them. The Voyager golden records contain sounds from Earth. Aboard both Voyager 1 and 2 are golden phonograph records, time capsules containing sounds and images from Earth. The contents were carefully chosen to represent humanity in our world. There are greetings in 55 languages, music from different cultures, natural sounds like thunder, wind, and birdsong, and even the sound of a human heartbeat. There are also images encoded on the record, showing scenes from Earth, human anatomy, and mathematical diagrams. The records are encased in protective aluminum covers with instructions on how to play them etched on the surface. It's unlikely any extraterrestrial civilization will ever find them, but the gesture is meaningful. It's a message in a bottle, cast into the cosmic ocean, carrying the story of who we are. Some moons orbit in the opposite direction. Most moons orbit their planets in the same direction that the planet rotates, but a few, called retrograde moons, orbit in the opposite direction. These are usually small, irregular moons, likely captured asteroids or comets rather than moons that formed alongside the planet. Triton, Neptune's largest moon, is the most significant example. It's large, geologically active, and has a retrograde orbit. This suggests it didn't form with Neptune, but was captured from the Kuiper Belt. Over time, Neptune's gravity is slowly pulling Triton closer. Eventually, in a few billion years, Triton will cross the Roche limit, the point where tidal forces will tear it apart, creating a spectacular ring system around Neptune. There are planets with 2 suns and moons with rings. The universe is full of configurations we've only recently discovered. Some planets orbit binary star systems, experiencing the light of 2 suns. Tatooine in Star Wars isn't pure fiction. Such worlds exist. And recently, astronomers discovered that some moons might have rings. Quaoar, a dwarf planet beyond Neptune, has a ring despite being far too small to hold one, according to previous models. If moons can have rings, the variety of planetary systems is even greater than we imagined. Each new discovery expands the possibilities, showing that the universe is endlessly creative. Solar flares can disrupt technology on Earth. The sun occasionally releases massive bursts of energy called solar flares, along with coronal mass ejections that send billions of tons of charged particles streaming into space. When these particles reach Earth, they can interfere with satellites, disrupt GPS signals, and even cause power grid failures. In 1859, a massive solar storm called the Carrington Event created auroras visible as far south as the Caribbean and caused telegraph systems to fail. If a similar event occurred today, it could cause widespread damage to modern technology. Scientists monitor the sun constantly, watching for signs of activity, and space weather forecasting has become an important field. The sun's activity follows an 11-year cycle, with periods of high and low activity. We're always at some level of risk, a reminder that we live within the sun's reach. Galaxies are moving away from us in all directions. In the 1,920 seconds, astronomer Edwin Hubble discovered that distant galaxies are moving away from us, and the farther they are, the faster they're receding. This was the first observational evidence that the universe is expanding, but it doesn't mean we're at the center. Every galaxy sees the same thing, all other galaxies moving away. It's the space between galaxies that's expanding, carrying them apart. Imagine dots on a balloon. As the balloon inflates, every dot moves away from every other dot, but no dot is at the center. The expansion of the universe works the same way, and it's accelerating. Driven by dark energy, a mysterious force we still don't fully understand. The surface of Mars is covered in iron oxide dust. That's why Mars is red. The iron in the Martian soil has rusted, reacting with oxygen in the thin atmosphere over billions of years. The result is a dusty, rusty landscape, covered in fine particles that get picked up by winds and scattered across the planet. Dust storms on Mars can grow to engulf the entire planet, lasting for months. These storms are powerful enough to obscure the surface completely, though they're not as dangerous as they seem in movies. The atmosphere is so thin that even high-speed winds carry very little force. But the dust itself is a problem. It coats solar panels, reducing their efficiency and posing challenges for rovers and future human missions. Mars is a dry, dusty world, but it's also geologically rich, with ancient river valleys, polar ice caps, and towering volcanoes. Some meteorites on Earth came from Mars. Over the years, a few meteorites found on Earth have been identified as Martian in origin. These rocks were blasted off the surface of Mars by asteroid impacts, traveled through space for millions of years, and eventually fell to Earth. By studying them, scientists can learn about Mars's geology and history without sending spacecraft. One Martian meteorite, ALH 84001, found in Antarctica, sparked intense debate in the 1,990 seconds when some researchers claimed it contained fossilized microbial life. The claim was controversial and has not been widely accepted, but it highlighted the possibility that life might have once existed on Mars. Whether these meteorites carry traces of life or not, they're invaluable pieces of another world delivered to our doorstep. Astronauts' hearts become more spherical in space. On Earth, gravity pulls blood toward the lower body, and the heart works constantly to pump it back up. In microgravity, this pressure is removed. Blood distributes more evenly, and the heart doesn't have to work as hard. Over time, the heart becomes slightly more spherical and loses some muscle mass. This can be a problem when astronauts return to Earth, as their hearts need to readjust to gravity. To counteract this, astronauts exercise for several hours each day, using resistance equipment to keep their cardiovascular system strong. The human body is finely tuned for life on Earth, and space presents challenges that require constant adaptation and care. The moon is moving away, and days are getting longer. As the moon drifts farther from Earth, about 3.8 centimeters per year, Earth's rotation is gradually slowing. This means days are getting longer, though the change is minuscule, about 1.7 milliseconds per century. Over hundreds of millions of years, this adds up. Fossil records show that Earth's days were much shorter in the distant past. Coral growth patterns from 400 million years ago suggest that a year had about 400 days, each lasting about 22 hours. Eventually, billions of years in the future, Earth and the Moon will become tidally locked, with one side of Earth always facing the Moon, just as one side of the Moon always faces Earth. But this is so far in the future that the Sun will likely become a red giant before it happens. Nebulae are stellar nurseries and graveyards. Nebulae, vast clouds of gas and dust, play two crucial roles in the life cycle of stars. Some nebulae are stellar nurseries, regions where new stars are born from collapsing clouds of gas. The Orion Nebula, visible to the naked eye, is one such place, glowing with the light of young, hot stars. Other nebulae are planetary nebulae, the glowing shells of gas ejected by dying stars. These mark the end of a star's life, beautiful and ephemeral, lasting only tens of thousands of years before fading. And then there are supernova remnants, the expanding debris from exploded stars, enriching space with heavy elements. Nebulae are places of transformation, where matter is recycled, where death gives way to birth, and the universe renews itself. The coldest temperature ever recorded on Earth was in Antarctica. In 2010, scientists measured a temperature of minus 93.2 degrees Celsius at a high ridge in Antarctica. This is the coldest natural temperature ever recorded on Earth's surface. It occurs during the polar winter when the sun doesn't rise for months. The air is dry, the sky clear, and heat radiates into space without being replenished. It's so cold that exposed skin would freeze in seconds, and taking a breath could damage your lungs. These extreme conditions make Antarctica one of the most hostile environments on Earth, yet it's still far warmer than many places in space. The surface of the Moon, for example, drops to minus 173 degrees Celsius during the lunar night, and in the shadowed craters of Mercury, it can get even colder. Earth's coldest places are balmy compared to the vacuum of space. Some galaxies have no dark matter. Dark matter is thought to make up about 85% of the matter in the universe, and most galaxies contain far more dark matter than normal matter. But in 2018, astronomers discovered a galaxy, NGC 1052 DF2, that appears to have little or no dark matter. This was unexpected and puzzling. If dark matter is essential for galaxy formation, how did this galaxy form without it? One theory is that it formed from materials stripped away during a collision between two larger galaxies. Another is that its dark matter was somehow removed. The discovery challenges our understanding and shows that galaxies are more diverse than we realized. The universe continues to surprise us. Comets have two tails, not one. When a comet approaches the sun, solar radiation heats its icy surface, causing gas and dust to be released. This creates two distinct tails. The dust tail is broad and curved, composed of small particles pushed away by solar radiation pressure. The ion tail is straight and narrow, made of charged gas particles pushed by the solar wind. Both tails always point away from the sun, regardless of the comet's direction of travel. This means that when a comet is moving away from the sun, its tails point forward, leading the way. Comets are often described as dirty snowballs, but they're also dynamic objects, constantly changing as they journey through the solar system. You could fit 1 million Earths inside the sun, with room to spare. The sun is enormous. Its volume is about 1.3 million times that of Earth. If you could hollow out the sun and pack Earths inside, you'd fit well over 1 million. Despite this vast size, the sun is not particularly dense. Its outer layers are tenuous, much thinner than Earth's atmosphere at sea level. Only the core is incredibly dense, where hydrogen is fused into helium under extreme pressure and temperature. The sun contains 99.86% of the mass of the entire solar system. Everything else, all the planets, moons, asteroids, comets, and dust, is just a rounding error. Jupiter's moon Europa may have twice as much water as Earth. Beneath Europa's icy crust lies a global ocean kept liquid by tidal heating from Jupiter's gravity. Some estimates suggest this ocean could contain twice the volume of all the water on Earth. It's one of the most promising places to search for extraterrestrial life in our solar system. The ocean is in contact with a rocky seafloor, where hydrothermal vents might provide energy and nutrients, much like the vents on Earth that support rich ecosystems in the deep ocean. NASA and ESA are planning missions to study Europa more closely, with spacecraft that could analyze the plumes of water vapor that erupt from cracks in the ice. If life exists in Europa's ocean, it would be one of the most profound discoveries in human history. Black holes can spin at nearly the speed of light. When matter falls into a black hole, it carries angular momentum with it. This causes the black hole to spin, sometimes incredibly fast. The spin of a black hole is measured by a parameter called A, which ranges from 0, not spinning, to 1, spinning at the maximum possible rate. Some black holes have been measured with spins near 0.9 or higher, meaning their event horizons are rotating at a significant fraction of the speed of light. This rotation drags space-time around with it, an effect called frame dragging. Near a rapidly spinning black hole, nothing can remain stationary. Everything is pulled along in the direction of the spin. This creates complex dynamics and can affect the formation of jets and the behavior of accretion disks. There are planets that orbit pulsars. Pulsars, rapidly rotating neutron stars, are among the most extreme objects in the universe. They're the remnants of supernova explosions, incredibly dense and bathed in radiation. It seems like an unlikely place for planets. Yet, in 1992, astronomers discovered planets orbiting a pulsar. These worlds are thought to be second-generation planets, formed from the debris of the supernova that created the pulsar. They're exposed to intense radiation and would be utterly inhospitable, but their existence shows that planets can form in the most extreme environments. The discovery of pulsar planets was also significant because they were the first confirmed exoplanets ever found, proving that planets exist beyond our solar system. The universe's expansion is accelerating. For most of the universe's history, the expansion was slowing down due to the gravitational pull of matter. But in the late 1990 seconds, astronomers discovered that the expansion is actually speeding up. This was a shocking revelation. Something is pushing the universe apart, and that something is called dark energy. It makes up about 68% of the universe and acts like a repulsive force, counteracting gravity. The nature of dark energy is one of the biggest mysteries in cosmology. It could be a property of space itself, or it could be something entirely new. Understanding dark energy is essential to predicting the universe's ultimate fate. Will it expand forever? Will it eventually reverse? The answer depends on the properties of dark energy, which we're only beginning to explore. Mars once had rivers and lakes. Today, Mars is a cold, dry desert. But billions of years ago, it had liquid water on its surface. Ancient river valleys, lake beds, and even possible shorelines have been identified by orbiters and rovers. The atmosphere was thicker then, warm enough to sustain liquid water. But Mars lost most of its atmosphere over time, likely due to the solar wind stripping it away after the planet's magnetic field shut down. Without the protection of a magnetic field, the thin atmosphere couldn't hold heat, and the surface became the frozen wasteland we see today. Understanding what happened to Mars helps us understand Earth and the conditions necessary for life. It's also a cautionary tale about how planets can change. Saturn's moon Enceladus has geysers. From cracks near Enceladus's south pole, plumes of water vapor and ice particles erupt into space. These geysers are powered by a subsurface ocean kept liquid by tidal heating. The plumes contain water, salts, and organic molecules, ingredients that could support life. Some of the ejected material falls back to the surface, while the rest escapes and feeds Saturn's faint E-ring. Scientists have analyzed the composition of the plumes using spacecraft, learning about the chemistry of the hidden ocean beneath. Enceladus is small, only about 500 kilometers wide, but it's one of the most exciting places in the solar system for astrobiology. You could walk to space in just a few hours. The boundary between Earth's atmosphere and space is not sharply defined, but it's commonly placed at the Kármán line, 100 kilometers above sea level. If you could walk straight up at a steady pace of 5 kilometers per hour, you'd reach space in about 20 hours. Of course, you can't walk up, and the journey would become impossible long before you reach that height due to lack of oxygen and extreme cold. But it's a thought experiment that shows how thin Earth's atmosphere really is. The protective layer of air that sustains life is just a delicate shell around our planet, fragile and finite. The Milky Way's supermassive black hole is relatively quiet. At the center of our galaxy lies Sagittarius A*, a supermassive black hole with about 4 million times the mass of the Sun. Compared to black holes in other galaxies, it's surprisingly inactive. It's not actively consuming large amounts of material, so it doesn't produce the brilliant jets and radiation seen in quasars. Occasionally, it flares briefly when it captures a passing star or cloud of gas, but most of the time, it's quiet. This is fortunate for us. If it were more active, the radiation might make large regions of the galaxy uninhabitable. We live in a relatively calm galactic neighborhood, far from the chaotic center. Earth is the only planet not named after a god. In our solar system, all the planets except Earth are named after Roman or Greek gods. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune all have mythological names. Earth, on the other hand, comes from Old English and Germanic words meaning ground or soil. It's a humble name for a remarkable planet. Perhaps because we've always lived here, we saw it more as the ground beneath our feet than as a celestial object. It wasn't until the space age that we truly saw Earth as a planet, a fragile blue sphere floating in the vastness of space. And so, our journey through space comes to a gentle end. We've wandered among stars and planets, through nebulae and galaxies, across the vast distances of the cosmos. Each fact has been a small beacon, a flicker of light in the endless dark, reminding us that the universe is vast, ancient, and full of wonder. Perhaps some of these ideas will stay with you, or perhaps they'll drift away like stardust, scattered across your thoughts. Either way, the universe will still be there tomorrow, patient and timeless, waiting for you to look up once again. If you're still awake, you're welcome to explore more. But if your breathing has slowed and your thoughts have softened, simply rest. Let the quiet of the cosmos carry you gently into sleep. You are part of this universe, made of the same atoms that were forged in stars long ago. You're connected to everything you've heard tonight, and to everything beyond. Sleep well, traveler, and good night.